So we've seen in chapter 5, when we were doing antiderivatives, I checked this on the test, which some of you knew, but some of you didn't. Products are notoriously tricky to do an antiderivative of. There's no such thing as multiplication in products. And so there's no such thing as multiplication in antiderivatives. So we have to have other ways to handle that. And I said, you will be able to do it, we just can't do it yet. And so 6.2, what we've done for the last 2 days, that was examples of products. When you see a product, one of the ways to run those products is use substitution, okay? But the problems you've been working on were specifically created so that use substitution always worked. But that's not always the case. So now we need to add into it, well, what if use substitution truly doesn't work? You've tried all the use substitution options and it's just not working. Then we add in U and V substitution. So it's a double substitution. One of the ways they call that parts, because there's multiple parts to the problem. We call it anti-differentiation by parts, but it's like I'll say, well, what was your U and what was your V? So you'll have both parts working at the same time. So this is another strategy to do products, because there's no such thing as the product rule. All right, that's what we're going to talk about today. Okay, we're going to look at how the product rule worked for derivatives. We'll look at why it fails with antiderivatives and how we do that differently. It also allows us to do antiderivatives of logs, which we've never done before, and antiderivatives of inverse, like sine inverse, tan inverse, arctan, that kind of thing. So this tool is really powerful, having both a U and a V at the same time. All right, so use your U substitution when you can write it with parentheses and it works out great, or if it's a product and it works out great. But if it doesn't, then we go to U and V together. All right, so let's review. How would you take the derivative of U and V? Okay, what is that going to look like? So if I take U times V, and I want to take the derivative, this is the notation, okay? We use Leibniz notation. Take the derivative of the product of U and V with respect to X. What does that turn into? Okay, can we use Leibniz instead of prime? So it starts with V and then times du dx. Okay, and plus U and dv dx. Okay, that's how we did derivatives. There's no nice, clean way. You okay, Evan? Yeah. You need like Tylenol or something? You're right? Okay.
No,
okay.
As long as you can.
Okay. All right, we're gonna just move things around. Okay, so in math, we're always allowed to like slide things over to the other side. So what I would like us to do first is just use the commutative property. So we're just going to move the whole left side to the right and the whole right side to the left. Okay, so just go with me. We're going to move those things over. So we're just going to put the v du dx plus the u dv dx on that side. And then we're going to have this on the other. Okay, so I'm just flip-flopping sides, which is totally legal in math. All right, another thing that's legal in math is subtraction. So I'm going to subtract a part from one side and then move it to the other side. So what I'm going to do is subtract this. So that will leave me with u dv dx by itself. And I'll have d dx of u times v minus v times du dx. Okay, again, all legal things that I'm doing to math here. Okay, the next thing I'm going to do is what I would do to any math problem that had fractions I didn't want. Do you remember how we've dealt with that in the past? Okay, right. Do these have a common denominator all the way through? Yes. What is it? Dx. Okay, let's get rid of it. So what would I do? Multiply everything by dx. So we're going to multiply this by dx, and we're going to multiply this by dx, and we're going to multiply this by dx. So we're multiplying everything by dx, which reduces a whole bunch of the dx's for us. And so I'm going to use just erasing to get rid of them. All right. The last thing I'm going to do is I'm going to do something to all, and as long as you do it to one side, what else do you have to do? I got to do it to the other. Okay, so what I'm going to do next is I'm going to take the antiderivative of this. So I show that by I'm going to take the antiderivative of this. On the other side, I'm going to take the antiderivative, and then I got to put parentheses because I'm taking the antiderivative of the whole side. Is it legal for me to distribute that integral symbol? Yes. Why? Because you can add and subtract integrals. And because this is a subtraction problem, it's legal for me to do that. So I'm going to go ahead and distribute. So I'm going to erase a couple of those, and I'm going to put an integral symbol there. So what I end up with is the integral of u with a dv attached to it, and on the other side, the integral of a d and then a uv product, and then an integral. So I have three different integrals. What's the integral, the inverse of? Right. What do inverses always do to each other? Right. Do you see any place where the symbol of an integral and the symbol of a derivative are present in the same part? Okay, right here. We have the presence of an integral and the presence of a derivative, a d, in the same position. So what do they do to each other? Okay, they negate each other. And so it's completely gone. And all I'm left with is that part has no integral left in it whatsoever. All right, this is the development of what we're going to be working with today. Okay, the format has two integrals, but then one section has no integral. This is where it comes from. You're not going to be tested on it. I just wanted you to know that it is mathematically provable. So go to the next slide and you'll see the same thing. This is the formula we work with. This mechanism will integrate almost any product you need if U substitution didn't work. U substitution is still your best friend, okay? That's still the one you're going to want to try first. But if U substitution doesn't work, then this method, called integration by parts, it's like we learned factoring, right? And factoring works great when the star method works out nicely and you can find the numbers that work, but then if it didn't, then you use the quadratic formula. Okay, so here's just another strategy. This setup here. Okay, we call this parts because there's a part that you call U, and then there's a part that you call V, and then you just plug all the other parts in. So I'll just show you the process and how it works. All right, in making your choice for U, there's a little acronym that helps you run through what's my best U possible, and it's called the Lippitt test. You know, in chemistry, you have the litmus test. You guys did that in chemistry. What is that test about a substance? Acidity, it's pH level, right? Whether it's an acid or a base, the litmus test. This is the Lippitt test, and every letter stands for something to help you go through. It's like we've done PEMDAS, and we do things like that just helps you keep things in order. All right, in this, L stands for logarithm. If there is any kind of logarithm in your problem, I don't care if it's a natural or any other kind of logarithm, that's going to be your number one choice for U. If you see a log, you're like, that's it. You're my U. It beats out everything else. Okay, so if you see a log, that's your U. I stands for inverse trig. If you don't see a log, but you do see an inverse trig, then that would be your second best choice for U. P is any kind of polynomial. Okay, so the polynomial could be a squared, it could be a cube, it could be a seventh power, it could even be a fraction power, okay, like a 2/3 or something with a power. So sometimes people also call this power option. Any kind of polynomial or power, that would be your third option for U. If you get to the bottom letters, you're really kind of scraping the bottom of the barrel. If you don't have any of those, okay, can you think of anything that starts with an E? Yes, exponential, I've heard that, okay. Exponential would be like an E or any other exponential. That would be your second to last option. And the very last option to pick is any regular trig. equation, like sine, cosine, tangent, or anything like that. Okay, these are your choices for u. Now I want you to really look at the key thing here at the bottom. Whatever you didn't pick for u, whatever is left over, okay, that leftover is called the part that is the dv part of the problem. So our whole problem is going to have 4 parts altogether. There's a u, there's a du, there's a v, and there's a dv. You pick the u first, and you actually pick the dv part as your next part. Let me show you how that works. All right. You'll see a little plus sign thing in your equation, or over on the side, and I put little backgrounds about what parts go where. Okay, this is clearly a product, and I already know that u substitution is not going to work. Okay, I picked this problem on purpose. Using the Lipit test, L-I-P-E-T, I need to pick one part of this product to be my u part. All right, do I have any logs in this problem? No. Do I have any inverse trigs in this problem? No. Do I have anything to a power or polynomial in this problem? Yes, I sure do. That would be the x. X to the what? X to the 1. That's still a power. Okay, x is a polynomial. It's a polynomial of degree 1, but x is still the polynomial. So your u, and so in that little plus sign, just put the x right there. That's what we pick. All right, everything else, okay, all the leftovers are the dv part of the problem. So everything else that was left, the cosine parentheses x dx, that is all the dv part of the problem. All right, those are the first 2 things you assign. So you just break the problem up into parts. That's why this is called integration by parts. Okay, if x is what I chose, then in this box I want for u, x is what I picked for u. Remember, this is what I picked for u. What is the differential that goes there? Okay, what is, or the derivative of x? 1. So that's what goes in that next box. Okay, the number 1, because the derivative of x is 1. I'll do it in red. Okay. Then I look at the cosine part. Cosine was what I picked for dv. Cosine is a derivative. If that's what the derivative is, what's regular v? If dv is cosine, which is the derivative part, what did regular v have to be? It had to have been sine. Okay, these are called the 4 parts that you need to make this integration work. All right, once you have that, and remember, maybe now that you've covered them up, I don't know, maybe you want to jot down what they were. This was u, this was du, this was dv, and this was v. Maybe you want to write those all there. Okay. All right, now the pieces are ready to be dropped into the formula. The formula says start with an antiderivative and start with u. Okay, I'm just following what's in the green box. So what was u? X. Okay, and then after that comes dv, and that was cos x dx. Okay, this is the problem I'm starting with. That is equal to u again, which is x, and v, which is what, according to my little chart? No, v, sine x, okay? And then minus, and then the integral, and then v, oh, Mrs. Pfeiffer, I've led you astray. It just was not thorough. It's not really 1. Shoot. Sorry. It was du dx equals 1. Du dx equals 1. So then what's du by itself? Right? If du dx equals 1, then dx by itself, du by itself is dx. Okay, I forgot to get that by itself. Okay. Now I'm going to put v next, which is sine x, and then du, which is dx. Okay. So I just plugged everything into the formula. One of those integrals has an answer. Which one? Yeah, sine x dx, this one has an answer. Okay, the answer to that, all right, so I have x sine x minus, all right, Rose, what is the answer to that? Negative cosine x and plus, because the answer to that, it has a plus c on it, right? Because it doesn't have bounds, right? Every time it doesn't have bounds, it's a plus c. So then my full answer is x sine x plus, you said, cosine x plus c. And that is the answer to the original problem we started with. By equality, we said, all right, here's my beginning problem. That's equal to the next step, which is equal to the third step, which is equal to the fourth step. So therefore, that must be the answer. Okay, in other words, I want you to really get this. All of this is the antiderivative of what we started with. How would you check it? If all of this is the antiderivative of this,
Can you take the derivative?
if you took the derivative of this, where should you end up back again? You should end up back here. And you do. If you take the derivative of this, and you take the derivative of this, and the derivative of c is 0, if you take the derivative, you end up right back at the beginning again. Isn't that cool how that works? All right, this just takes a little practice. Now, sometimes this helps to see this visual. You're going to combine that first. Okay, that's going to be the first combination because u and v are always combined first. That's this part right here. And then you're going to combine these two second. That's the second part of the combination. So sometimes that helps to like see that visual, to remember, oh, diagonal first and then across the bottom. All right, let's try again. All right, I'm using integration by parts because this is a multiplication problem. Multiplication problems don't have their own antiderivative. They need help. So we're going to help them out by using the Lippitt test, and we're going to assign the parts. Okay, does anybody want to jump in with what they think u should be assigned as according to the LIPET order? U is x again. Okay, power, p comes before exponential, which means this is dx. All right, everything else that wasn't already chosen is part of the v, and then its antiderivative. Okay, so now I got to remember how did I do an antiderivative of e to the negative x again? Okay, well, it is itself, but what else is involved in an antiderivative? Divided by what two things? The natural log of e, and divided by what else? The chain rule of -1. All of that is involved. So I'd probably just clean that up, and I go, oh, the natural log of e is already 1. So I'm just going to clean that up and put a negative right here. So just to summarize, to get from this box to this box, we do derivative. But to get from this box to that one, we're doing the antiderivative. Once we've done that, we're ready to combine diagonally the combination of those parts. So my problem, which starts as x e to the negative x dx, this is the problem I have assigned, is equal to the combination of x and negative e to the x, so that would be this, minus the integration of the combination of these two, and the integration of the combination of that would be negative e to the negative x dx. And that one, that last integral, should always be possible. Okay, it should always be a possible integral for you to do. So you just clean up now at this point. What might we like to do with this little integral right here, or this little negative sign? Yeah, pull it out to the front. If we pull that out to the front, then that allows me to have a plus out here, which I like better. So my answer is going to start with negative x e to the negative x, and then plus the antiderivative, which again, e to the negative x has the antiderivative of an ln e and a minus 1, and then plus c. So I would probably clean up my natural log of e and then ultimately put negative like that. Okay, that is the antiderivative of the original problem. And you can check that by taking a derivative again and hopefully get back to the place you started at. The rest of the lesson is going to be me doing more and more examples with you, just so you have a chance to see a little bit of everything. Are there any fundamental questions right now? Like, wow, I just don't even understand what you're doing at all. Yeah, Rain.
If like the u was a exponential, would you plug in the u in the exponent or the entire thing, like the number x exponent?
So in other words, there's no L for logs, there's no I for inverses, and there's no P for polynomials. Yeah, we're gonna do one of those. Yeah, I plan to do one of those. So let's try one. Let me see which one that's gonna be. That might even be. That's gonna be tomorrow. So for tonight, everything you have is gonna have either an L, an I, or a P in it. Okay, and then we'll get to the block earth. Yeah, tomorrow we'll do those. Okay, let's try another one then. Okay, there's no way to do an antiderivative of a logarithm without this method. Okay, there's no way to do an antiderivative of a logarithm. All right, L-I-P-E-T. All right, Sydney, you want to pick? Okay, yes, L for logarithm is the first one. So what would you choose for your U? Yeah, ln of x is what I choose. And then the derivative, do you remember how to do the derivative of ln of x?
Is it ln x times ln times dx?
You're close. You're close. I think you're trying to do the antiderivative of it. The derivative. There's something divided by. Yeah, there's some kind of division going on there.
Is it 1?
Okay. It's 1 over. Nope, you're doing the exponential one. It's just 1 over x, okay? For logarithms, yeah, it's hard. I know they're all can be. Okay, so it's 1 over x. But then we have to do the chain rule. And the chain rule is, because this has parentheses, it would be the chain rule of what was inside. So dx, right. All right, remember, that is a derivative. Okay, now, what's, Sydney, the only thing left? Yeah, dx is the only thing left. And what is the antiderivative of dx? Regular x. Okay, that's the antiderivative. Okay. So the question, which started out as ln x dx, becomes the correct combination of the parts that we've identified. So we've identified these parts. So that's going to start. So that would be, typically you'll put the x in front of the ln of x. That's just a cleaner way to write it as opposed to the ln x in front of the x. And then minus, okay. And then this one will be the combination of these two. All right, so minus the integral of, and then what happens in that green box when we combine those two things? We just get dx. And remember, that last final integral should always be something you know how to take the antiderivative of. So we have x ln x minus the antiderivative of dx, which is just x itself, and then plus c. and that's your antiderivative. Mm-hmm.
So if you're taking if you're doing a UV substitution,
Mm-hmm.
would your U always be like the first portion?
No. The U has to still follow the LIPET rule. So sometimes they give them to you backwards.
Okay.
Okay?
So like because they're products, you can.
Because it's a product. Yep, products are commutative, so any order is fine. Okay, here's another one. This is an LIPET again. There's no other way. So I'll say, hey, try the Lipit test. Okay, Nick, pick your U. Log base 5 of x, okay? So the log base 5 of x is our u. So then we need the derivative of that. So the derivative is going to be a fraction again, just like we saw last time. Here's, I think, where you were thinking about that extra ln. Why didn't we need that extra ln last time? Do you remember why? It really was there. You were saying it. It really was there, but it's ln what? That was ln e, and so I kind of just skipped over that. This one is going to have that extra ln, so it's 1 over x, and then it's ln 5 because of the log, and then the chain rule of dx. Okay, so if log base 5 of x was what Nick chose, I'm just going to literally even cross it all out. We've already used it, and the only thing that's left is dx, so that's my final part, or my dv part, and the antiderivative of that is x again. Okay, I didn't put, yeah.
Oh, why is the antiderivative of dx and x? Because I thought it was like dx over dx.
Mm-hmm. These are differentials, not derivatives, so they're a little bit different. So because we know that dx equals 1, right? Do you remember that? Like we've just been reducing that. Okay, so right now all we have is just, we don't have the full part, we only have a differential, which is dx, which has an antiderivative of just x. Okay, all right. Now, I didn't write for you the format, so you're going to have to start working towards memorizing it. So this was log base 5 of x dx, that was the question, must be equal to. Okay, and the combination is this combination first. So typically you'll put the x in the front, and then the log base 5 of x, minus the integral of this combination next. Now notice when you do that combination, what do you see happens? Say it again. Okay, but what reduces when you combine those? The x's reduce. We're left with 1 over ln 5, and then dx is what's left. But what kind of number is 1 over ln 5? It's a constant. Where should I put that? Okay, so I'm going to put that out in front. So let's swap those and pull 1 over ln 5 out to the front. So then I just have a constant sitting in front of that. So I'll have x log base 5 of x minus the constant 1 over ln 5, and then the antiderivative of dx, which, as Ethan just pointed out, is x itself, plus c. See how I told you like this lesson was, these lessons are all just mechanics, 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 skill, skill, skill. We'll put it into context of what it means when we do some word problems with these. Okay, try again. L-I-P-E-T. Okay, Edson, how about giving it a try? What do you want to pick? According to the Lipit test, what would be your U?
Sine inverse of x.
Yep. All right, sine inverse of x. And if I literally cross all that out, the only thing other than that left is dx. That's all that's left. All right, so I got to do my derivative. And maybe you're thinking, blast, I got to remember the derivative of inverse sine now? Okay, all right, yeah, Gotta remember the derivative of inverse sine. The derivative is 1 over something. What's 1 over what? The square root 1 minus x squared, and then the chain rule derivative is dx. Okay, and the other one, it's the antiderivative, which is just x. Okay, we're ready to combine. All right, green light means go. Let's try this. So the problem started out as the inverse sine of x dx, which must be equal to the combination diagonally of x sine inverse of x minus the integral of the combination horizontally of these two. Now, what do you notice doesn't happen? Nothing reduces. So what I'm left with is an x numerator, a square root denominator, and a dx. But Mrs. Pfeiffer promised that every single integral at the end is possible to work out. So how do we work it out? We got to go back to yesterday's lesson. Because how could we rewrite that?
We can't just take the derivative of the antiderivative of 1 over square root 1 minus x squared.
Not with an x there. So this is x parentheses 1 minus x squared to the negative half dx. It's possible to do that. It's got parentheses in it. This just takes us back to Friday and yesterday. Okay, so to do that, we need to go back to traditional u substitution. So the traditional u substitution would say, what would you pick for u? 1 minus x squared. And then we do du dx is negative 2x. So we work out all the cross multiplication and all that. So I'm just going to do all that. So dx by itself is 1 over 2x du. Negative, thanks. Negative 1 over. All right. So it builds. These are not, the skills you learn are not isolated. So in parentheses, I replace u. And the dx at the end, I replace with negative 1 over 2x du. Now I'm to the point, oh, now the x's reduce, because they didn't reduce before. In the yellow, there was nothing that reduced, but now the x's reduce. And what can I pull out to the front of my integral? A negative 1/2, which combines with the negative that's already there. So we'll have x sine inverse of x plus 1/2 on the outside of u to the negative 2 du. All right, now I can do that integral by raising, what? Oh, yes. Sorry, I had it written right. This year's talking about the power. There, thanks. Okay. So now I'm going to do the antiderivative on that. So add 1 and divide by the new power. All right, see if I can fit all this on here. All right, so I have a half. I have u, which is now going to go up to the higher power of positive 1/2. But what else do I got to do? Multiply by 2, which ultimately reduces with the 1/2 out front, and then a plus c. So my final answer will be x sine inverse plus u to the 1/2, which is the square root of 1 minus x squared, and then plus c on the end. Okay, those are some doozies because it's all combined. This is a great homework question, okay? Because you got the time to work on it. It's not so great of a quiz question, not so great of a test question. It just takes too long, but it's a really good homework question for you to dig into. All right, one more. L-I-P-E-T. All right, Lauren, pick us our U.
X
X squared?
X squared.
Okay. All right, what were you hesitating about?
The exponential, but that's later.
Yeah, the exponential does come later. Okay.
The constant.
Okay, yeah, the constant maybe gives you a little hesitation. It does not matter if you want to put the constant with your x squared or if you want to put your constant with your 2e to the x. It's not going to change the order of the question. Typically, I would put it here with my first one. Okay, but it really is not going to, it's a constant, it's not going to affect it. So then the antiderivative of that is going to be 2/3 x cubed. Sorry, I'm doing the wrong column for the antiderivative. The derivative of that would be 4x and then dx on the end. Okay, so then if we've already used the 2, then that leaves e to the x dx here. And the antiderivative of e to the x is e to the x divided by the natural log of e times the chain rule of 1, so just e to the x. Okay, Lauren did a good job. All right, she's passing it to Evan. Okay, one corner of the room to the other. All right, Evan, take it away.
So then we have e
Okay,
to the
I'm going to write, you talk, I'm going to write the problem. So 2x squared e to the x dx must be equal to, okay.
equal to e to the x times 2x squared.
Okay, so I'm going to put that in this order. Okay,
Minus the integral of e to the x times du,
which is,
4x dx.
okay, so 4x e to the x dx. Okay, Mrs. Pfeiffer promised that that integral would be possible, and it is. But you got to do integration by parts again. Okay, it is possible. You just got to do it one more time. Okay, so let's pass it to Juliet. Juliet, now for that problem, for the 4x e to the x, what would you pick for your u there?
4x.
Okay, she picks 4x, which means that e to the x dx is the leftover. Okay, and then how would you fill in the bottom of that little part, that bottom squares?
Du would be 4x.
4 with a dx, good.
And then b would just be e to the x.
Okay, good job. Okay, passing it over to Reagan. All right, Reagan, do it for the combination for that one.
Integral 4x dx equals 4x times ex
Okay, 4x times ex, okay.
minus 4 or e to the x 4 dx.
Minus the integral of e to the x times 4 dx. I'll put the 4 in the front like that. Okay, now she said that that came from this integral right here, and she is totally right. That integral, where I drew the green arrow from, produced all of that. But what's in front of that integral? Okay, this is the equality. This is, okay, what's in front of all of that? This stuff we had from before, that carries down. And what else carries down? The subtraction. And so the subtraction has to impact all of what Reagan said. So that subtraction gets distributed. So I'm at 2x squared e to the x minus 4x e to the x plus, and I might want to pull the constant 4 out in the front. Okay. And once again, we're finally to, but Mrs. Pfeiffer promised I'd be able to do this integral. Can you?
Unfortunate.
What's the antiderivative of e to the x?
E to the x.
Do I need anything fancy to do that? No. The antiderivative of e to the x is itself e to the x. So we have 2x squared e to the x minus 4x e to the x plus 4 e to the x plus c how would you check your work?
Take the derivative.
If you took the derivative of the 3 parts of your answer, you would end up back at the beginning again. Okay, one thing you might notice, what do those terms all have in common with each other? Besides even e to the x, what else? And a 2. So you might see this written this way. So if they take the 2 and the e to the x out, you would be left with x squared minus 2x plus 2, and then the plus c would be on the end. So you might see the answer written that way as well. That is an equivalent answer. Okay? Yeah, Chloe.
Where does the 4x dx from the integral come?
You're talking about this part right here?
No. Like
No,
where
okay.
the green arrow's pointing.
Oh, that came from this first combination here. Of the second time we did it. So like this combination here, Chloe, produced that one, okay? And then the horizontal combination produced that one, which had to be redone. And then we do another diagonal, which produces that one. We're getting them all, okay?
Too many diagonals.
Too many diagonals.